Howdy, everyone, and particularly howdy, Judy, that I see in the comments. Welcome back to the channel. I am Professor Parks, and today I am continuing with my lecture series. I am going to be talking specifically about uh, what causes the seasons and why astrology, if it were to be considered a science, why it has some fundamental flaws to it. But before I begin, um, I would like to give you fair warning. Um, I am feeling much better than I have been before, but I just decided to stay home today. One of the things I wanted to tackle was a pound of laundry that my cat is now guarding. Um, but other than that, what I'm trying to say is that I'm using a different setup. Um, one of the things that I wanted to do with this particular lecture series, and here's the other cat trying to come into play. Um, One of the things that I was wanting to do with this was to experiment with the idea of using different types of software, particularly simulations, to really get my point across. I've been using PowerPoints for so long, and I find them to be a bit dry and uh, I think, limiting. I think they might can be a bit limiting in terms of visualization. So I'm going to be trying things out. Now, because of all that, and because I'm home, I have to use my Mac, which is why the camera looks a little bit weird, and the sound might be a little bit weird. I don't know, but I have to use my Mac. Now, I've been at this for about 30 minutes, and apparently, Stellarium on Mac is. I've been having tech issues, so this could be fun. And by fun, I mean frustrating, but I hope it's fun. All right, so where was I going with this? So last time I talked about, I want to start off by sort of recapping what I talked about in the last lecture, which is navigating the night sky. And I wanted to use Stellarium. So if you're not familiar with Stellarium, bad timing, but Craig's internet is acting up anyway. All right. Is FTFE going live right now? Anyway, um, where was I going with this? So one of the things I was talking about last time, just to recap, was talking about navigating the night sky. Specifically, what does the night sky look like at any given point in the night or day, and specifically your location. What is it that you can? With Witsit. Oh, all right. I'm going to let that wash over me. I have some very personal feelings about Mr. Witsit, particularly after some. Anyway, um, so night sky, um, and particularly showing you what the night sky looks like from various points on the Earth and at various times of the year. And so let's just jump into it. If you're not familiar with the program Stellarium, you can go to it by stellarium.org. Let me put this in the chat. Stellarium.org. Stellarium is a program which is free to use, free to download, free to install. It works on Windows machines. It works on Macs. It theoretically works on Linux, but for some reason, my Linux box and Stellarium don't like each other today. But if you don't want to install it or what have you, there is a web-based option available if you just kind of want to play with it. It is a fabulous tool. If you ever have a question of, hey, if I go outside right now, could I see a planet? Could I see Jupiter? And Stellarium can tell you. Or if you have the question, when is Jupiter? When can I go outside next? If Jupiter is not in my sky, when is it going to be in my sky? Stellarium can answer that as well. So let me actually change this a bit. I have it. Like I said, I was playing with this prior to coming on, so I want to kind of reset where I'm at. Perfect. Come on. There we go. Want to go there. Thank you. All right. Let's pop this up. Oh wow, the newest thing is okay. No, I'll do that. I will address that all after the lecture proper. So here we go. So I've loaded up Solarium. Hopefully you can see it in some detail. What I'm looking at here is this is the night sky. If I were to walk outside, this is what the night sky would look like, assuming it was clear, which it currently is not. Overlaid on that is a grid of the horizontal system or the horizon system, the alt-as system. So you can see, let me see if this works. There we go. This is my horizon. If you remember that that has an altitude of 0. This is my zenith, the point directly above my head that has an altitude of 90. And then each one of these lines, these vertical lines reaching from the zenith down to the horizon, is my basically measures of azimuth. So, but there you go. So this is what my night sky would look like in terms of tonight. And so you can see Mars is pretty much directly overhead. Capella, which is a bright star in the constellation of Auriga, that's what it is. You got the moon down here. Well, let me show you something. Whoops. Come on, stupid Mac. Let me forward this in time, if I can, without the Mac getting nuts. Come on. Okay, so it's going in real time. There we go. That's what it looks like. So let's face south. And so this is what my sky looks like as the night progresses. The moon, for example, let's look at the moon. The moon, for example, is going to get up in the east, and then it's going to transit right about there. Well, actually about there. Let's put south there. And then the moon is going to go down here, as you can see there. Now let's actually flip this around. Let me pause this for a moment because the sun's coming up. Let me swing this around to north. So we've got due north. And so I am currently, like I said, I am at a latitude of about 38 degrees north. So if I were to look 38 degrees north, thereabouts, this is 10, I think this is, 10, 20, 30. I'm assuming you can see my cursor, and 8. That is, as you can see in the upper left, that is Polaris. So let me go. So I've shown you the alt-as system, but let me really show you the other coordinate system that I talked about last time, which was right ascension and declination. And that is the equatorial system. And so now let us look at, really should share the program rather than the screen, but oh yeah, it's going this way because I forgot I'm going north. So you got west on the left, east on the right. Ah, I knew this was going to go wrong. Oh. All right, so you can see the stars are arcing across the sky. You can see again the moon is over there. Moon is over there arcing. You can see Arcturus. Let's follow Arcturus. Arcturus is coming up and coming down. So let's pause this for a bit. Let's say I honestly I don't know where you're at, Judy. So I am just going to go to somewhere that I would like to go, which is I don't know if it's. I don't know what the latitude on that is. So actually, let's go to. Let's be controversial. Let's go to Moscow. The United States? No. All right. So all I've done here is Finland. Okay, Finland. I have to admit, wow, this is embarrassing. I don't know what the capital of Finland is. Wow, that is just so friggin' American of me. How about Arvik? Let's do it. Finland. Helsinki. That's the capital, right? All right, let's go with that. All right, so all I've done is I moved our location to Helsinki, Finland. I haven't changed the time. I haven't basically the universal time, and so Judy can confirm. Well, right now actually, I've messed with the time. Here, let's set the time. So the time is today is the 6th. And the time is it's 7:40 p.m. Yeah, there we go. Thereabouts. 2:41 local. Okay. Is that right? Well, so here is what the night sky at 2:30 would look like for Judy. And oops. Here is what the night sky looks like for me. Now, you can see that Vega was over here. Right now, I can see the moon, and I believe Judy cannot if we're at the same location. And so this is to illustrate, hopefully to illustrate a little bit more, a little better about the fact that if you're in a different position on the Earth, then you're going to see the night sky differently at the same time as someone else. Now let's go to a sort of a radical extreme. Let us actually go to, I think it was Roque last time was in Argentina. So let us go to Buenos Aires. So again, I haven't changed the time. I have simply changed the location. And right now we are looking due north at Buenos Aires. The moon for me is going to be at this time would have been up here. For Roque, it will be down here. He can see they can see Rigel right there. But one of the things that they can't see, for example, is let us. There we go. Search window. Polaris would be below Roque's horizon. And so you can see from the equatorial system, as before, you saw that for me and for Judy, the point of the north, the point of the North Celestial Pole was somewhere around here. Now you can see that the North Celestial Pole is actually below Roque's horizon. However, you have the South Pole, you have the Southern Pole. So Roque can see the southern stars. So you have, and also they can see a lot of stars that we cannot, like Achenar and Rigel, Centaurus. Canopus, I cannot see from Fairfax, but actually from Atlanta, Georgia, you can barely make out Canopus at the highest point. So that's kind of what I wanted to show you in terms of sort of a recap of what we were talking about last time. Actually, let me do this really quickly. Um, location. Uh, hmm. South Pole? South Pole telescope. That'll work. All right. I'm going to do this. So basically, we are looking straight up. Oh, sorry, motion sickness. So if we were located at the South Pole, which obviously wouldn't have trees and stuff, and you were to look up at the night sky, basically right now at this time of night at 13 hours UTC, or no, excuse me, at 11, 12, we've kind of gone off. But if you looked at basically down, if you were down there right now, this is what you would see the night sky do. This is, you see the night sky would orbit around or seem to revolve around a common point directly over your head. And the stars would neither rise nor set. Now, as I go to Quito, Ecuador, if someone wants to put in the chat what the name of a star is that neither rises nor sets and can be seen in the daytime, or it can be seen in the night sky, if you could put that in the chat, I will come back to it. Because there's a particular term for it. Now let's go to... Yes. Oh, I'm failing at this. I think that's close enough. Actually, let's just do this. Actually, Judy, you're close. It's circumpolar rather than coplanar. Hey, that'll work. Okay. So this is if we were seeing the sky in, this is if we were seeing the sky, if we were on the equator. And now you have west on the right hand side of the screen. You have obviously east on the eastern half of the screen, or the east on the west or left hand side of the screen. You can see now that the stars are rising in the east, going overhead, directly overhead, and going to the west. At this point, there are no circumpolar stars. Every star in the sky is going to rise and it's going to set. There's nothing that you can there's nothing that you can see all throughout the entirety of the night when you are on the equator. Now, on the equator, as I mentioned before, the equator has the nifty ability that if you were to let me make sure I've got that right. No, actually, I'm going to back way off that statement. I think last time I said that if you're on the equator, you can see every star in the night sky, over the course of a single night. And that is wrong. I was very, very wrong about that. What I was envisioning was that would be true if the sun were not, in fact, up in the sky. Which brings me to my next point. So let's go back to Fairfax. Let's go back home for me. All right. So let's look at the constellation of, and again, we're looking south. Let's look at this constellation right here, which is Orion. And right now, it is December 7th. Now, instead of progressing in time as in minutes, seconds, hours, let's step forward even faster. Let's step forward in terms of days. So basically, particularly if I stop this, oh man, really should have. Max, that stupid dock. Okay, now I have stopped it. Now I've stopped time. Dun, 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 Thanos like. So every time that I move essentially the sky or change the sky, what I'm going to be doing is I'm going to be stepping in days. The time of night is always going to be 6:04 p.m. for me. And what we see, and you can do this on your own, and you can see this effect yourself if you were to go outside, find a constellation that you normally see, or even find a star that you can readily identify every time, and you were to take some fiducial point, say a tree outside your house, and you were to look at where that star was at 6 o'clock at night relative to that tree every night over the course of, I think you would even be able to see this over the course of a week, probably even a couple of days. Let's see. Here we have the next night. We have the next night. And you can see that if you were to take, say, the position of Betelgeuse relative to the horizon, for example, hopefully you can easily see that it is moving subsequent every night at the same time of night, 6 p.m., at the same time of night, Betelgeuse is going to be in a different part of the sky. Until eventually, it isn't in the sky at all. This demonstrates to us that there must be some other motion going on in there must be some other motion going on in the universe that affects our view of our night sky. So obviously our rotation will affect the view of where stars are at any particular time of day on any particular day. We also know that depending on where you are on the Earth, the pattern, the different stars that you can see is also going to change, basically due to your local horizon. But now we see that depending on the date, not the time of day, but the date, the pattern or the stars that we see in the night sky are going to be different. Now, let me do this again, I'm doing this for visualization purposes. So let me make this as visual as possible. These are the constellations. And I'll put in the, so now let's concentrate on Bootes or Biotes, I believe is the actual pronunciation of it, this one here. So now we're at, instead of February, now we're in June. And so you can see that during this time at 6 o'clock, Orion is no longer in our night sky. And if I were to advance in time, in terms of the night's minutes and seconds, you can see that, or you can hopefully see that since Orion has set in the west, over the course of the night, Orion is not going to show up. It's not going to appear. And what that thing that flew by, that was AIS TechSat 3. Anyway. So what is it? What is it that causes? So obviously rotation isn't what's causing us to see these stars differently. Obviously, it's not rotation that is causing us to be able to see Orion in one time of year and not in another time of the year. That has to do with our motion around the sun. And so for me, if someone were to ask me, how do you know that the Earth is moving? Two very obvious signs for me are that the stars rise in the east, set in the west, and that our stellar patterns, the constellations that we can see, are different based on are different over the course of a single year. And so I'm going to use a different program to really illustrate that. But let me diverge a little bit, or let me take a tangent for a moment with you while I have this program up and talk about astrology. Now, those of you who are not familiar with how astrology works, at least the very, very basic principles of it, astrology purports that there are 12 constellations, and depending on where you were, where the sun was, which constellation the sun was in, let me back that up. Just kind of lost my train of thought mid-thought. So astrology basically concentrates on 12 constellations, which they refer to as the zodiacal constellations or the zodiac. These, and they claim that there are 12 of them. They also claim that depending on where the sun was in the night sky, where the sun was, which constellation the sun was in upon your birth, that essentially dictates your personality. That gives you an overall sense of who you are and how you will live your life. And then they get even more funky in that they supposedly can predict your day and your future based on where the stars and the planets are going to be in relation to these constellations. Well, for one thing, let me see if I can illustrate this. The zodiac or the zodiacal constellations are those constellations which, you know what? I may have to go into settings. I thought this was a fairly easy show, but I thank you for bearing with me. Again, this is sort of you all are being guinea pigs for how I do this. Zodiacal lights, markings, Skylore. All right. Hopefully, I could just basically show you this from the hand. So the zodiacal constellations are those constellations through which the sun passes. So we have, let me show you the constellation art. So let us go back to today, or in or abouts today. Oops. Close enough. So the sun, if I were to put the sun's path up on here, which I know you can do, but honestly, I've forgotten how to do it, and I don't want to spend too much time trying to search for it. But the sun's path, if you'll just simply trust me, is the sun would go through Virgo, it would go through Leo, Cancer, Gemini, Taurus, and then so forth and so on. So the 12 zodiacal constellations, let me see if I can get them. Virgo, Leo, Cancer, Gemini, Taurus, Aries, Capricorn, Scorpio, Libra. All right, Libra. Did I mention Sagittarius? Sagittarius. Virgo? No, I already said Virgo. There are two more. Can't remember what they are. Not the point. Astrology tells me that there are 12. But astronomy tells me something different. Let's go back to here. Yeah, there we go. We got Virgo. Now, let's see if I can actually illustrate this without it failing completely. It should be fun. All right, let's go to noon. Where's the sun? Where did the sun go? Oh, I've got it set. All right. Now I got to find the sun. Where's the sun? All right, let's do it this way. Well, I know now that if I'm going to do this again, I am going to have to have this more scripted. Are you not showing me the sun? Okay. Oh man, I don't think I can show this to you appropriately because for some reason it's not showing me the sun, where the sun is. All right. Oh well. So I will just basically give you spoilers on it. The first reason why that I know what I'm going to do because this is bugging me. What I'm going to do is I'm going to put out a very a short video, not live stream, but I'm going to put out edit together a short video that shows you. I'm going to figure out how to do it, and I'm going to show you through Stellarium what I'm about to say is true. What I'm going to say is that there are not 12 zodiacal constellations. There are actually 13. The 13th zodiacal constellation is actually a little guy. Well, I guess he's a big guy. Actually, let's do it this way. So about mid-screen, you can see Gemini, Cancer, Leo, Virgo coming into view, Libra. Dun, dun, dun. So I'm pretty sure Scorpio is one of them. Yeah, Scorpio. So if you were to look at the sun, it's not in it very far, very long, but the sun would pass through Virgo. It would pass into Libra. And then for a very short time, it would pass into this constellation right here called Ophiuchus, and then into Scorpius. So there are people who are born where the sun was in the constellation of Ophiuchus. So they are Ophiuchans. The other problem that astrology has is that they're wrong. When I am my birthday is in March, late March. So I am technically in Aries. I am an Aries according to an astrologer. But, and again, I will show this in the video that I will make. But if you were to use Stellarium, you were to go back to my date of birth, and you were to actually see where the sun is at my birth, what you would find is that the sun is actually in the constellation of Pisces. And that is because there is this thing called precession. Now here, I think I'm going to actually, again, if you can bear with me, I am going to open up my slides. Recent. All right. Again, if you could bear with me. Cygnus, I saw your question. I will answer it just after I'm able to get this going. I want to make sure. Lecture 6. That doesn't make any sense. All right, let's open this up. Yep, that'll work. That will work. Okay, put that over there. All right, you can see this. So, I'm not going to go into presenter mode, but I am going to just go through this. Zodiac. There is something called precession. And what's remarkable to me is that Hipparchus, the gentleman who actually cataloged the entire sky, as I mentioned the last time, he cataloged the entire sky in terms of the positions of stars and their magnitudes. He was able to actually see that the North Celestial Pole wasn't always in the exact same position, because the Earth wobbles like a top. And what that means is that the Earth has an axial tilt of 23.5 degrees. If you think about the universe or the solar system in 3 dimensions, that means that axial tilt is going to be pointing off somewhere into space. Right now, the axial tilt happens to correspond such that the North Celestial Pole is pointed right at the star of pretty much right at the star Polaris. However, as the Earth is going around the sun like this, if you can see me in the corner, it's also precessing around like this as it does so, but it does that very, very slowly. So obviously it goes around the sun once every year. It goes around it wobbles on its axis, or wobbles around its axis, arcs out a circle once every 26,000 years. Now, while that is a very long time, we have been around long enough to actually see this effect. And again, Hipparchus apparently managed to be able to tell this. He wrote, he commented on the fact that the North Celestial Pole appeared to move, I guess, within his lifetime. So if we look at this, this is the arc of the North Celestial Pole as it goes around, or as it is going around the night sky. If you are able to live for 26,000 years, you would be able to see this effect. Right now, like I said, the North Celestial Pole is 25,760 years, so not quite 26,000 years. So you see that this is basically right here. Hopefully, you can see my cursor. This is where the North Celestial Pole is currently at. Polaris is right there. But in 6,000 years, it's going to be somewhere within the constellation of Cephus. But eventually, the best star, the brightest star that's going to be even anywhere reasonably close to the North Celestial Pole is going to be the star Vega in the constellation of Lyra. Right now, Vega is basically directly overhead during the summer months. But you can see here, all right, so you have Polaris is there at 1 AD, basically the time of Christ, the time of the Roman Empire. The Romans did not see Polaris as the North Celestial Pole. The Romans, when they looked up, they could see Polaris actually marking out a circle going around empty space. So again, while 26,000 years or 25,760 years might seem like a very long time, in the span of human experience, it's short enough that we can literally see this happening, given sufficient records of astronomical records. Now, this is what I was talking about in terms of that whole Zodiac business. So you can see here, Ophiuchus is down here. It's not technically part of the official astrology, so it doesn't have a part of the Zodiac. But if you are born between November 30th and December 17th, congratulations, you are an Ophiuchan and your future is unknown. I was a pair. I am technically an Aries, but as it happens, if you put my birthday in here, I am technically a Pisces. So I'll just put this up for a second and let you guys kind of figure out, hey, I'm not this, I'm that. While you're doing that, I'm going to first answer Real Cygnus's question. Are there any better tools? Are there any better tools that pros use that you're aware of that happen to be free and or open source? Now, my question to you is tools for what specifically? If you're looking for a planetarium program, if you're looking for something that will map out the sky at any particular point in the Earth for any particular day, then Stellarium is where you want to go. That is what literally what professionals use if they want to visualize it in that way. If you're talking about data reduction programs, if you're talking about you have digital images that you want to stack, you have digital images that you want to extract data from, then I would suggest Astro Image J. But there are a couple of those. So really, it really depends on what sort of tools you're looking for. Can you use Stellarium for aiming your telescope? Not as far as I know. I've never tried to use it. For us, we use the Sky program. And I will say that I will have to look into it. There might be a way to do it. There might be a way that Stellarium is what we call ASCOM compliant. ASCOM is basically a generic framework that it's sort of plug and play. If you have programs that are ASCOM compliant, then you can use ASCOM to basically control your telescope, your dome, your camera, so forth and so on. So if Stellarium is, and your mount is, your telescope is, mainly your mount, then yes. But I haven't actually looked into it, to be honest with you. Like I said, we use the Sky, which is definitively not free. The Sky X Professional is somewhere in the range of $500-$600, maybe a little bit more. And you need the professional version in order to control telescopes, from my understanding. So, sadly, no. Now I'm again. I beg your pardon. I am going to try something new again to illustrate yet another program that's out there. This is not free, but it's about $30 thereabouts on Steam, and I might be able to do this. Let's try doing it this way. Okay, hold on. Go away. Sure, it can access that. Oh, you can hear it. And taking that off. Present. Screen. Stop. Screen. All right. Present. Share screen. Window. Entire screen. Let's go over here. There we go. Close. Continue. Whatever. There we go. Share. No, no, that is not what I want. That is what I want. Haha. K-Stars. Yes, that's for that's a Linux-based program, isn't it, George? Sounds like a Linux-based program. This program is called Universal Sandbox. Now, it is fantastic for some things, not so fantastic for others. If you want a good visualization of the 3D solar system, it's fantastic. if you want a good visualization of, say, exoplanets, of um, of exoplanets going around other host stars, fantastic. If you want something that is scientifically accurate, very accurate, and you're dealing with, say, um, galactic collisions or anything, or even stellar evolution, not so much. Main reason for that is computational power. This is a program designed to be run on personal PCs. If you are interested in things like what are the stars going to do when two galaxies smack together, that work has typically been done on supercomputers. You need that kind of processing power. It's only now where you can do heavily constrained simulations of galactic mergers on a very, very powerful desktop machine. So why am I showing you this? Well, I'm showing you this because I think it's pretty awesome. I'm showing you this mainly because what I want you to get a sense of, and I think that, what I want to get you get you in the mindset for is to think in 3 dimensions. When we look at the night sky and we think of the Earth, I think it's very common or natural to really just kind of assume that, all right, the Earth is moving around the sun and it's doing so in a loop. But that's not quite true. So if we look here, so we have the inner solar system, we have the Earth over here. I'll zoom in a little bit. So we got Mercury doing its thing, we got Venus doing its thing, we got Earth doing its thing, and they're all moving around in roughly circular orbits around the sun. And when we think of these things, that's kind of, and when I present later information about, say, orbits, I'm going to present it in pretty much in this way, a top-down view. But that's not the only way to view things. The other way to view it is edge-on. And what we see, these lines, each of these different lines corresponds to a particular orbit. And you can see that the Earth and the Venus and Mercury are not what we call coplanar. There is a certain amount of tilt with respect to each of the different planets. And we'll explore that more. And you can see that Mercury is, in comparison to the Earth, is way more ecliptic than anything, or way more inclined than, say, Venus is. Now, the other thing I want to use this for, and before I go back to my slides, is, whoops, can I come back? No, too close. Is you see that the Earth is revolving around the sun. What I want you to think about is, and actually I am going to see if I can catch the Earth. All right, let's do this. Let's pause. That way I'm not trying to click on an immovable object. All right, I'm going to center on the Earth. So now, in a sense, the Earth has become the center of the solar system. Everything is revolving around it, which I guess from a relativistic point of view is kind of true. So if I were to do this, and I were, basically what I'm trying to do is I'm trying to show you that there's the sun. What I want you to focus in on is the background stars. Hopefully you can easily notice that the background stars, the stars behind the sun with respect to the Earth, are changing constantly as the Earth goes around the sun. And that is what causes that apparent change between from what we can see in summer to what we can see in winter. All right. Yeah, I'm really going to have to rethink. Whoops. What do I want to do here? Rethink this sort of presentation, but hopefully it was not as clear as mud. What I want to do now is I want to open this up because it's getting late and I do want to get to the seasons. So Mm-hmm. Current slide. I think I'm good, actually. Nope. Sharing the wrong screen. Hey, Dr. Clive, how are you doing? Let's share that. So let's go back to the sun. Excuse me. Let's go back to that movement of the sun, or rather, the movement of the earth. Excuse me. Oh. So when we talk about one of the consequences of the fact that the Earth is revolving around the sun, you can see this in timing, and because of you can see this in timing. So you might think of yourself, you might think to yourself, oh, if someone were to ask you how long a day was, you would simply just answer 24 hours. Well, that's not true. Well, it is true in a certain sense, and it isn't true in another. It really depends on what you define as a day. If you're talking about a terrestrial day, what we normally think of a day, what you're really talking about is a synodic day, or the time it takes to go from the sun directly overhead at noon to the sun directly overhead at noon again. That is 24 hours. But if we're talking about a particular star, like I said, I always default back to Vega. If you were to find out how long it takes for the star Vega to go from directly overhead all the way around back to directly overhead, you would find out that that was 23 hours and 56 minutes. That is the true rotational period of the Earth from a sort of absolute perspective. That is that is the that is the rotation period as taken from the frame of the stars, which we can, to first order, assume don't move, that they are fixed in space. So it's a fixed coordinate system. So the Earth actually rotates once upon its axis, not on 24 hours, but once every 23 hours, 56 minutes. The next question, of course, is why is there a difference? Why is it that there is 4 minutes discrepancy between if I measure a star going from the meridian all the way around to the meridian to when the sun goes from on the meridian all the way around back onto the meridian? Again, this shows us that there is an additional motion that the Earth goes through that isn't rotation, that has to do with the fact that the Earth revolves. Now, this is hopefully, I don't know if you can see it very well, but so you have the sun here. Whoops, I think I have to go over here. Yeah, you have the sun. No, you can't see my cursor. Anyway, you have the sun, it's the yellow ball, and then the gray ball, which is directly over to your left. That's the Earth. That's their starting point. That's t=0. Now, if you were to wait 23 hours and 56 minutes later, then what you would find is that the Earth has moved in its orbit. And now this star, which was, if the sun weren't in the way, would have been directly overhead, is now directly overhead again. But the sun would be off to the side. It takes the Earth an additional 4 minutes to rotate the observer such that they are back under the sun again. And that is why there is a difference between a synodic period and a sidereal period. One way to kind of see this for yourself, if you have the equipment, is if you have a telescope mount, or if you have a mount and you try to track the sky. If you try to track the sky such that the rate is 15 degrees per hour, your stars are not going to stay in your field of view. They're going to trail, because the actual rate you want to use is a little bit less than that. It's actually 360. It's 360 degrees divided by 23 hours 56 minutes. So yeah, that is yet another way you can see the difference between a synodic period and a sidereal period. This slide is just basically telling you, showing you, showing you the difference between the sun on, or why we see different patterns of stars or constellations of stars due to why we see different patterns of stars over the course of a year, for example. Mainly because if you're here over here in March, the sun is in the way, so you wouldn't be able to see Pisces, Sagittarius, Pisces, Aquarius, and Capricornus. But in September, you can see these constellations because the Earth or the sun is going to be on the other side of the Earth. Now, what is it? Now, the title of this lecture was, in fact, Seasons. So let's get into that. But wow, I've been at this for an hour. All right, let's get into this. And what are the seasons, or what causes the seasons? The seasons obviously are the overall trend for the temperature to get higher or lower, and also our days and nights to be of different times. If you were to ask the general public, you would get probably somewhere fairly quickly, you would find someone, if you were to ask them what causes the seasons, they would tell you, well, distance. Obviously, if we are further away from the sun, it's going to be winter. If we're closer to the sun than we are, then it's going to be summer. That illustrates a certain bias. And that bias is you're forgetting that you're on a globe and that not everyone lives in the same hemisphere that you do. Because if it were summer, if the distance to the sun was the issue, if you are close to the, if I in North America were experiencing summer and I was close to the sun, then why is it that folks in Australia experience winter? So distance isn't the answer. The main answer is the fact that, again, the Earth is tilted. The Earth has an actual tilt of 23.5 degrees. If we did not have an actual tilt, we effectively would not have seasons. The reason why the axial tilt matters, the reason why it causes the seasons, is because of the angle at which light hits the Earth. And that is directly related to how much energy is imparted to the Earth's surface. So temperature is a measure of how much energy is received, or you can think of temperature as how much energy that something is getting. Something is getting a lot of temperature or a lot of energy, then it's hot. If something is getting very little energy, then it's cold, typically speaking. Now, you can get energy. The amount of energy that you receive is dependent on two things. One, how much energy there is to receive in the first place. And two, the angle at which you receive it. Let's take this experiment. This thought experiment. Take a piece of cardboard, cut a hole in it. You take a piece of cardboard that's, say, in this case, it's actually, let's say it's 3 meters in 3 meters square. So it's a big piece of cardboard. And you were to cut a hole in that cardboard that was 1 meter squared. And you were to hold up that, and the sun is, say, directly overhead, and you were to hold up that cardboard, then you would get on the ground would be projected light of approximately 1 meter squared of light hitting the ground. So that the amount of energy is going to be that the total amount of energy that you would receive over 1 square meter. The total amount of energy that you receive is basically constant everywhere on the Earth. But if you were to tilt that cardboard or if the sun were a different part of the sky, then what you would see is that the light comes in an indirect angle or an oblique angle. And so the projection on the ground gets larger. So in this example, we have, instead of 16.5 degrees giving us a square area of energy received of 1.04 square meters, now we have an incoming angle of star or sunlight at 63.5. And you can see now that the area which the area upon which that same amount of energy is being received is now 2.34 meters. What that means is that in those two particular places, the places where the sun's energy is concentrated over approximately 1 meter, that's going to be a hotter place than an area receiving the same amount of light from the Earth or from the sun, but it's projected over 2 meters or 2.5 meters. Let's see. Yeah. Angle schmangle. So yes, so that is essentially one of the reasons why we have different seasons, Hopefully, if we go back to here, what you can see here is, let's say that with this, we have that the Earth's axis, you're standing in Europe, for example. You're Judy, you're in Finland. Here, the light is coming from the right. You can see that it's hitting Finland roughly perpendicular to the globe, to the surface of the Earth. And so in this, which would be considered summer for her, the amount of area, the amount of light is constrained in a much smaller area. And so she gets more, the temperature will rise commensurately. But if we were to go to Rogue, for example, and live in Antarctica, hopefully you can see that the incoming rays of light, all of these rays would be parallel. The incoming rays of light would be more oblique or would be at an angle. And so, therefore, people in the southern hemisphere experience winter. There's another cause or another consequence of there's another consequence that contributes to the fact that the days are hotter in the summer and the days are colder in the winter. Like I said, as I've been saying, in the summer, the starlight is more, or the sunlight is more direct, which is going to cause things to heat up faster and to a larger extent. But there's also something else, and that has to do with what we were talking about before in terms of where the stars are relative to your position. During your summer months, the sun is going to be in the sky for longer than it would be in the winter months, because it is going to be higher up in the night sky. Or, excuse me, it's going to be higher up in the daytime sky. This is a figure which we refer to as the analemma. The analemma is a bit complicated, but really what I want you to focus in on with this figure 8 image is the positions of each of those dots. Each of those dots corresponds to an image of the sun, or the location of the sun, at a particular time of day. Let's say, for argument's sake, noon. So a person went out to this particular location, which has a particular longitude and latitude on the Earth, and every day at noon, on particular days at noon over the span of a year, I think these are probably separated out by a couple of weeks, they measured where the sun would be. And so each of those dots corresponds to where the sun would be at that point. So let's say we're facing south. So east is on the left, west is on the right. The sun at the highest point, in the upper left-hand basically portion of figure 8, hopefully you can imagine that the arc in which the sun would have to travel is going to be much larger than the arc at which it travels if it were on the lower right-hand side of the analemma. So not only is the sunlight more indirect in winter, but the sun is not up for as the sun is not in the sky nearly as long. And so not only is it more inefficiently giving off energy or imparting energy onto the surface, but it's doing so for less time. And those are the two primary reasons or mechanisms for why the axial tilt explains our seasons. Now, I will, just to end this to finish this up, I will say that distance is a factor. Distance does play a factor in the seasons because of the fact that, yes, if you are closer to the sun, obviously you're getting more light, you're getting more energy from the sun than when you are further away. What that does is it doesn't really cause seasons so much as it causes a change in the extrema of seasons. So for the Earth, for example, at the present moment, the northern hemisphere is actually, the Earth is actually closest to the sun in or around June. Now, backing that way off, the Earth is closest to the sun in or around December, January. That is when we have, the northern hemisphere folks, have their winters. It's furthest away in June when we have our summer months. The reason for that is because the Earth orbit is not circular; it's actually slightly elliptical, and I'll explain that in greater detail when we start talking about orbits. So, what does distance? How does distance play into it? How does this small effect happen? And really, it is a very small effect. The change in distance between what we call perihelion when it's closest to aphelion when it's furthest away is about 3%. So it's a relatively small effect. What that boils down to is folks in the northern hemisphere have cooler average summer temperatures and warmer average winter temperatures than folks in the southern hemisphere. So if you're in Australia, because Australia needs to be even more dangerous or more extreme, people in Australia experience hotter summers as a function of latitude than people in, say, Europe. They experience colder winters than they would with people in corresponding latitudes in Europe. So if you're living at 40 degrees latitude south, your summers are hotter, your winters are colder than someone who lives at 40 degrees north. And so yeah, and that is where I'm going to stop it. I think, yes, that is where I'm going to stop my lecture today. Honestly, I've got to say, I'm not really thrilled with my performance today. So what I'm probably going to do, particularly for those of you who are in my class, I think I'm going to redo this lecture. Oh, good Lord. There we go. I think I'm going to redo this, or at least come up with a much more streamlined, much more more concise explanation for seasons and the Zodiac. But hopefully you got some of it. Hopefully you got some of it out, because I really do want to provide better visualizations than simply just PowerPoint presentations, and I have a couple of simulations in mind for that. But take-home points here are: if you want to have evidence, rather, or see an effect that is due to the revolution of the Earth around the sun, you really need to go no farther than why do we see different constellations in the sky at different times of the year, and why is there a difference between the sidereal rate, or how fast the stars move across the sky, as opposed to how fast the sun moves across the sky? So, oh, Bev, oh, good Lord. Anyway, yeah. So thank you all for being here. Thank you all for watching. Like I said, I hope you found this enjoyable. I hope you found this informative in some way. Again, I want to kind of go back over this because I think I rambled too much. And anyway, but the next what is my next lecture going to be on? Let's find out. My next lecture will cover. We'll cover the laws of planetary motion and basically the laws of planetary motion. We're going to basically cover the beginnings of the Copernican revolution. What was the model that was used, the mathematical model that was used in a predictive way to describe a geocentric universe when the Earth was the center of when the Earth was thought of to be the center of the solar system and the universe? What that model was, what its deficiencies were, and why it was that, what was the motivation to switching over to the heliocentric universe, and how that heliocentric universe model made by Copernicus was then perfected by Kepler. So, all right. All right. See you all later tonight. Oh, I forgot. If you do like this, please like, share, and subscribe as always. And also, if you want to help me out, Judy is my new patron. You can find my Patreon on my home YouTube home place, and please consider donating. All proceeds from my Patreons go to helping our outreach program here at George Mason, our student organization, and also our outreach programs, where I, for example, take our portable planetarium out to elementary schools, and for elementary school kids to experience what it is to have a night sky that isn't light polluted. Please consider it. All right. Well, apparently my internet is dying. So again, thank you all. Clear skies. And peace out.